In the summer of 1887, in the basement of a dormitory at Western Reserve University in Cleveland, Ohio, two men prepared to prove something everyone already knew. Light, the fastest thing in existence, required a medium to carry it. Just as sound waves travel through air and ocean waves through water, light waves must travel through something. They called it the luminiferous ether, an invisible substance that filled all of space, weightless, frictionless, permeating everything, your body, this room, the vast emptiness between stars. The ether was physics. It was as fundamental as gravity, as accepted as atoms. And these two men, using the most precise measuring instrument ever built, were about to detect it. To measure our motion through this cosmic ocean, to prove, once and for all, that the ether was real. They found nothing. It was the most famous failure in scientific history. A catastrophic null result that didn't just fail to prove the ether existed, it forced us to realize that our entire understanding of space and time was wrong. To understand why the Michelson-Morley experiment was so devastating, we must first understand the world it was meant to confirm. The year is 1887. Queen Victoria sits on the throne of an empire that spans the globe. In laboratories across Europe and America, physicists are putting the final touches on what they believe is a complete theory of the universe. Newton's mechanics explained motion with clockwork precision. Maxwell's equations unified electricity, magnetism, and light into a single, elegant framework. The great edifice of physics seemed essentially finished. This wasn't arrogance. It was earned confidence. These theories built bridges that stood, engines that ran, telegraphs that spanned continents. But there was one piece of the puzzle that everyone knew must be true, even though no one could quite explain it. In 1801, Thomas Young had proven beyond doubt that light was a wave. When he split a beam of light and recombined it, the waves interfered, creating bright and dark bands that could only result from wave motion. But here was the problem. Every wave needs a medium. Sound travels through air. Remove the air, and sound cannot propagate. Ocean waves move through water. What, then, carried light? The answer seemed obvious. There must be a medium, something that fills all of space, something through which light waves could propagate at their measured speed of 186,000 miles per second. They named it after the ancient Greek concept, the ether, the quintessence, the fifth element, beyond earth, air, fire, and water. And slowly, as the 19th century progressed, the ether became more than hypothesis. It became necessity. James Clerk Maxwell, perhaps the greatest physicist between Newton and Einstein, had unified electricity, magnetism, and light into four elegant equations. These equations predicted that light was an electromagnetic wave oscillating through space at a specific speed, approximately 300,000 kilometers per second. But speed relative to what? Every speed is measured relative to something. When we say a train moves at 60 miles per hour, we mean relative to the ground. The ground moves around the Earth. The Earth orbits the Sun at 18 miles per second. The Sun travels through the galaxy. Everything is moving. Speed is always relative to a frame of reference. But Maxwell's equations gave an absolute number for the speed of light. Not light moves at 300,000 kilometers per second relative to just 300,000 kilometers per second, period. To the physicists of the late 19th century, the answer was clear. Maxwell's equations must give the speed of light relative to the ether itself. The ether must be the absolute frame of reference for the universe, the fixed cosmic background against which all motion could be measured, which meant something remarkable. As Earth moves through the ether, orbiting the Sun at 18 miles per second, we should feel an ether wind, a cosmic breeze blowing past us as we sail through space. It would be subtle. Light moves so fast that even Earth's rapid motion would only change its apparent speed by about 1 part in 10,000. But it would be there, detectable, real. And if it could be detected, it would prove everything. It would confirm that the ether existed, that Maxwell's equations were complete, that the architecture of reality was exactly as physicists believed. The question became, could it be measured? That was when Albert Michelson built something extraordinary. Albert Abraham Michelson was born in Prussia in 1852 and immigrated to America as a child. By his 30s, he had become obsessed with a single question: how fast does light travel? At the United States Naval Academy in Annapolis, Maryland, in 1879, he had measured the speed of light to unprecedented accuracy, 186,350 miles per second, with an error of just 30 miles per second. But accuracy wasn't enough for Michelson. What he really wanted was to detect the ether wind. In 1881, in Germany, he attempted his first measurement. The idea was elegant in its simplicity. Imagine 2 swimmers racing in a river. Both swim at the same speed. One swims upstream for 100 feet, then back downstream to the start. The other swims directly across the river, perpendicular to the current, and back. Who wins? Common sense says they tie. Same distance, same speed. But that's wrong. The swimmer going upstream and downstream takes longer. The current slows him on the way up more than it speeds him on the way back. The cross-stream swimmer wins, not by much, but measurably. Michelson's idea was to do the same thing with light. Split a beam in 2. Send one beam in the direction of Earth's motion through the ether. Send the other perpendicular. Recombine them and look for the difference. The instrument he built was called an interferometer. Light from a single source would hit a half-silvered mirror. Part of the beam would pass through, part of the beam would reflect. The 2 beams would travel along perpendicular arms, bounce off mirrors, and return to be recombined. If they took different amounts of time, if the ether wind affected them differently, the waves would be slightly out of phase when they recombined. This would create an interference pattern, alternating bright and dark bands called fringes. Rotate the entire apparatus 90 degrees, and the fringes should shift. The beam that was going with the ether wind would now be going across it, and vice versa. It was brilliant, elegant, foolproof. Michelson saw nothing. No fringe shift, no evidence of the ether wind. But the null result didn't convince anyone. The apparatus was too sensitive to vibration. The measurements were uncertain. Perhaps he'd made an error. Leading physicists urged him to try again, with better equipment, with more care. So Michelson did something few scientists would dare. He decided to build an experiment so precise, so carefully controlled, that no one could question the result. An experiment that would either prove the ether existed or prove that the foundations of physics were built on sand. Edward Williams Morley was everything Michelson was not. 20 years older, trained as a chemist, methodical where Michelson was inspired, patient where Michelson was restless. They made an odd pair, but they shared something essential. Both men worshipped at the altar of precision. Between 1885 and 1887, they collaborated on smaller projects, confirming earlier measurements, refining techniques, building trust. And all the while, they were planning something larger. The interferometer they would build for the ether detection experiment would be, quite simply, the most sensitive measuring device ever created by human hands. First, they extended the light paths. In Michelson's 1881 attempt, the beams traveled about 1 meter before recombining. This time, they would use multiple mirrors to bounce the light back and forth, extending the effective path length to 11 meters, 36 feet. This amplified any difference the ether wind might cause. It was like comparing two swimmers racing not 100 feet, but 1,100 feet. The difference becomes harder to miss. But sensitivity creates a new problem. Any vibration, any thermal expansion, any stray air current would produce false signals far larger than the real effect they were trying to detect. Morley had the solution. They would mount the entire apparatus, mirrors, beam splitter, light source, on a single enormous block of sandstone. Not just any sandstone, a carefully chosen piece, precisely shaped, its surfaces ground flat to within a fraction of a wavelength of light. This framework would float in a circular trough filled with mercury. Mercury, liquid metal. The stone would rest on its surface like a ship on water, perfectly level, rotating smoothly on a central pin, immune to vibrations that would shake a normal table to pieces. It was beautiful. A machine that looked like Victorian engineering, but thought like modern physics. 5 tons of sandstone floating on mercury, measuring the universe to 1 part in hundreds of millions. But even this wasn't enough. They installed the apparatus in the basement of the dormitory, where temperature variations would be minimal. The heavy stone walls absorbed vibrations from street traffic, from footsteps, from the wind itself. The basement was closed off, sealed from drafts that might create thermal currents in the air. For weeks, they refined the setup, aligned mirrors with obsessive precision, tested the rotation mechanism, verified that the sandstone slab could turn smoothly through a full circle without disturbing the optical path. By the spring of 1887, they were ready. The calculation of what they should see was straightforward. Earth orbits the Sun at about 30 kilometers per second. If there's a stationary ether, we must be moving through it at least that fast, probably faster, since the Sun itself is moving through the galaxy. At 30 kilometers per second through a stationary ether, the expected fringe shift from rotating the apparatus would be about 0.4 fringes. Not huge, but easily visible to a trained observer looking through the telescope. And there was a bonus. They didn't need to guess Earth's direction of motion. They could measure at different times of day, at different times of year. Earth's orbital motion would add to or subtract from the Sun's motion through the ether. The signal would vary in a predictable pattern. Spring was particularly favorable. In April, Earth's orbital velocity would add to any motion of the solar system through the ether. On April 5, 1887, they began formal observations. The procedure was meticulous. Rotate the apparatus slowly, noting the position of the fringes at every 22.5 degrees. Complete a full rotation, then do it again, and again. Average multiple rotations to eliminate random errors. They worked through April, then May, then June, July. 6 turns every session, 20 sessions total, 120 full rotations of the apparatus, each carefully documented. The expected signal was 0.4 fringes. Clear, unmistakable. The proof everyone was waiting for. The observed signal was 1/40th of that. perhaps 0.01 fringes. Perhaps. Maybe. Within experimental error, it was 0. In August 1887, Michelson wrote to Lord Rayleigh, one of the most respected physicists in England. The experiments on the relative motion of the Earth and ether have been completed, and the result decidedly negative. Decidedly negative. Not inconclusive, not uncertain, decidedly negative. There was no ether wind. At least, none they could detect. And they could detect almost anything. In November 1887, they published their results in the American Journal of Science. The tone was measured, careful. They acknowledged their bewilderment. The interpretation of these results is that there is no displacement of the interference bands. The result of the hypothesis of a stationary ether is thus shown to be incorrect. Incorrect. The scientific community didn't know what to do with this. The most obvious conclusion, that the ether didn't exist, was unthinkable. It would mean throwing out huge portions of physics. It would mean light waves somehow propagated through absolute nothing. That Maxwell's equations had no physical basis. Unthinkable. So, physicists did what physicists do when experiments contradict theory. They created more elaborate theories. In 1889, George Fitzgerald in Ireland proposed something extraordinary. Perhaps objects actually contract in the direction of their motion through the ether. Contract by exactly the amount needed to make the null result appear. It sounds ad hoc, like inventing epicycles to save the Earth-centered universe. But Fitzgerald showed it could work. If the ether's electromagnetic forces caused material objects to shrink along their direction of motion, the contracted arm of Michelson's interferometer would perfectly confidently for the light delay caused by moving through the ether. A few years later, Hendrik Lorentz independently proposed the same idea. He called it local time and length contraction. He even derived exact equations that are now called the Lorentz transformations. These weren't random guesses. They were sophisticated theoretical frameworks that preserved the ether while explaining the null result. But here's what's fascinating. Lorentz and Fitzgerald were trying to save the ether, to keep physics as it was, to avoid revolution. They succeeded brilliantly at the wrong goal. Because what they actually did was hand the next generation the mathematical tools they would need to overthrow everything. In 1905, in Bern, Switzerland, a 26-year-old patent clerk named Albert Einstein was thinking about light. Not about ether, not directly about the Michelson-Morley experiment. Einstein was after something deeper, a problem that had troubled him since he was 16 years old. Maxwell's equations were beautiful. They predicted light as an electromagnetic wave traveling at a specific speed. But those equations didn't change when you switched reference frames. Unlike Newton's laws, which worked the same in any steadily moving frame, Maxwell's equations seemed to single out one special frame where the speed of light was exactly 300,000 kilometers per second. This bothered Einstein deeply. He once told a friend he'd been thinking about a problem since adolescence. What would it look like to chase a beam of light while traveling at the speed of light? According to classical physics, you should see the light wave standing still beside you, frozen in time, like a still photograph of an ocean wave. But Maxwell's equations said that couldn't happen. A stationary electromagnetic wave makes no sense. The equations simply don't allow it. So which was right? Classical physics or Maxwell? By 1905, Einstein had decided. Maxwell was right. Completely, absolutely right. The equations didn't need modifying. Our concepts of space and time needed modifying. He made two postulates, two assumptions from which everything else would follow. First, the laws of physics are the same in all inertial reference frames. This was Newton's relativity principle, extended to electromagnetism. No experiment done inside a sealed lattice can tell you whether you're at rest or moving at constant velocity. Second, the speed of light in vacuum is the same for all observers, regardless of the motion of the light source or observer. That second postulate sounds innocent. It's devastating. If the speed of light is always the same, not relative to some ether, but relative to every observer, no matter how they're moving, then something else has to give. Imagine you're standing on a train platform. A train rushes past at half the speed of light. As it passes, someone on the train turns on a flashlight. You, on the platform, see the light spreading out in all directions at 300,000 kilometers per second. That's what Einstein's second postulate says. The speed of light is constant for you. But what about the person on the train? According to Einstein, they also see the light spreading out at 300,000 kilometers per second, in every direction, even though they're moving. This seems impossible. If you're both right about the speed of light, something else must be wrong. Time. Time is not universal. Time is not absolute. When the person on the train measures 1 second, it's not the same as when you measure 1 second. Their clocks run slow compared to yours, or yours run slow compared to theirs, depending on perspective. And distance contracts. The train is shorter in your frame than it is in the train frame. These aren't tricks of measurement. They're real, fundamental, woven into the structure of space-time itself. When Einstein worked through the mathematics, he found that the equations were already known. They were the same length contraction and time dilation that Lorentz had proposed to save the ether. But the meaning was completely different. Lorentz said, objects really contract when they move through the ether, and time is affected by some unknown ether interaction. Einstein said, there is no ether. Space and time themselves are relative. Length contraction and time dilation are inevitable consequences of the constancy of the speed of light. Same equations, completely different physics. Lorentz preserved the ether and made reality complicated. Einstein eliminated the ether and made reality elegant. Here's what's remarkable. Einstein may not have even known about the Michelson-Morley experiment when he formulated special relativity in 1905. His famous paper, On the Electrodynamics of Moving Bodies, doesn't mention it. He built his theory from pure thought, from the incompatibility between Maxwell's equations and Galilean relativity, from his own teenage thought experiments about chasing light beams. But once the theory was complete, the Michelson-Morley results suddenly made perfect sense. From Einstein's view, there's no ether to move through. The apparatus isn't moving through any cosmic medium. It's just an apparatus at rest in its own reference frame. In that frame, the frame co-moving with the apparatus, the result is trivial. Of course, both beams take the same time. They travel the same distance at the same speed. Why would they be different? Rotate the apparatus? Still nothing changes, because you're still in the same reference frame. The null result isn't a puzzle. It's obvious, expected, natural. Now look from a different frame, say, the sun's rest frame. From this perspective, the apparatus is moving at 30 kilometers per second. Does this affect the measurement? Yes. Length contraction makes one arm of the interferometer slightly shorter. Time dilation affects when the photons arrive. But, and this is beautiful, these two effects exactly cancel each other. Not because nature is conspiring to hide the truth, but because space and time are structured this way. The cancellation is inevitable, built into the geometry of space-time. The null result isn't a failure to detect the ether. It's a demonstration that there is no ether, that the speed of light is absolute. When Einstein first described relativity in 1907, 2 years after his original paper, he finally mentioned Michelson and Morley. But not as inspiration, as confirmation. Michelson and Morley's experiment, he wrote, had actually shown that phenomena agree with the principle of relativity. The most famous failed experiment in physics didn't fail at all. It succeeded in answering a question no one knew to ask. Not, does the ether exist, but what is the nature of space and time?
Albert Michelson never accepted Einstein's relativity. He had spent his life making measurements of exquisite precision, measurements that revealed the universe as it truly was. Or so he thought. In 1907, he won the Nobel Prize, the first American to receive it in science. But the citation didn't mention the 1887 Aether experiment. It honored his general work on precision measurements and spectroscopy. Perhaps that was fitting, because by 1907, the Aether experiment was beginning to mean something Michelson never intended. Einstein's paper was slow to gain acceptance. Between 1905 and 1910, many physicists still preferred Lorentz's ether-based interpretation. The two theories made identical predictions. Why abandon the familiar ether for this strange new geometry of space-time? But gradually, the elegance of Einstein's approach won out. Not because it predicted different results, but because it was conceptually cleaner. It required fewer assumptions, no mysterious length contractions caused by unknown forces, just geometry. By the 1920s, the ether was dead. Not proven non-existent. You can't prove the non-existence of an invisible, undetectable substance, but unnecessary, superfluous. The luminiferous ether had joined phlogiston and caloric in the graveyard of discarded physics concepts. Michelson continued his work. He used his interferometer to measure the diameter of distant stars, the first time anyone had measured the size of a star other than the sun. He established wavelengths of light as standards for defining the meter. His instrument had failed in its original purpose, but succeeded brilliantly in a dozen others. In 1931, when Einstein visited Michelson on his deathbed, Michelson's daughter reportedly begged Einstein not to get her father started on the subject of the ether. Michelson died believing that light must propagate through something, that empty space couldn't be truly empty, that there must be a medium. He had spent his life proving the opposite, and never knew it.
But let's be clear about what Einstein's relativity destroyed, and what it preserved. Newton's mechanics didn't die. For objects moving much slower than light, it remains perfectly accurate. We still use it to calculate orbits, design bridges, predict trajectories. What died was Newton's absolute space and absolute time. The cosmic clock that ticked the same for everyone. The fixed stage on which physics occurred. Maxwell's equations survived intact. Not a single symbol changed. They already contained relativity. Einstein just revealed what was hidden in them all along. What died was the interpretation. The idea that these equations described vibrations in a material medium. That light was literally a mechanical wave in a cosmic jelly. The ether didn't die because it was proven not to exist. It died because it added nothing. Every phenomenon that seemed to require it, the propagation of light, the constancy of light's speed, electromagnetic induction, could be explained more simply without it. But something deeper was happening. A revolution in how we think about the universe. The 19th century understood physics as mechanics. Everything was pushes and pulls, gears and waves, tangible things in definite places doing definite things. The ether fit this worldview perfectly. Light as a mechanical wave in a mechanical medium. Reality as mechanism. The 20th century discovered something stranger. Reality isn't fundamentally mechanical. Fields aren't vibrations in stuff, they are the stuff. Space and time aren't the stage where physics happens, they're part of the show, dynamic and flexible. The Michelson-Morley experiment marked the transition between these worldviews. The last gasp of mechanical philosophy, the birth cry of modern physics. And it did something even more profound. The Michelson-Morley experiment teaches us something crucial about how science actually works. Michelson and Morley set out to prove what everyone knew was true. They built the most precise instrument in history to detect what everyone was certain existed. They failed. And that failure was worth more than 1,000 confirmations. Because science doesn't advance through experiments that confirm expectations. It advances through experiments that surprise us. Through null results that force us to question assumptions so basic we didn't even know we were making them. This pattern repeats throughout history. The ultraviolet catastrophe that led to quantum mechanics, the orbital decay that should have happened but didn't, leading to Bohr's atom, the neutrino experiments that showed neutrinos change type. Failure in science is often success wearing a disguise. But there's something else, something about Michelson himself. He spent his life making measurements more precise than anyone thought necessary. Why measure the speed of light to 5 decimal places when 3 would do? Why build an interferometer sensitive to fractions of a wavelength? Because precision reveals truth. If Michelson had been content with good enough, the null result would have been ambiguous. Perhaps the ether wind was just smaller than expected. Perhaps Earth dragged some ether along with it. Perhaps the effect existed, but was masked by experimental error. But Michelson's instrument was so precise that the null result was undeniable. Not maybe 0. 0 within 1 part in 100 million. That precision eliminated wiggle room. It forced the crisis. It demanded explanation. And ultimately, it gave Einstein the confidence to be radical. When Einstein proposed special relativity, he wasn't guessing. He wasn't speculating. He was building on bedrock. The Michelson-Morley null result wasn't ambiguous. It wasn't maybe. It was certain, undeniable, a foundation you could construct a revolution upon. Without that precision, Einstein might have hedged, added caveats, softened his claims. Instead, he wrote, "The ether is superfluous. Not might be, not appears to be, is." That certainty, that ability to dismiss an entire concept everyone believed in, came from Michelson's obsessive precision. This is what great experimental physics looks like. Not flashy, not quick, not easy. Obsessive attention to detail. Elimination of every possible source of error. Measurements so precise they leave no room for doubt. Michelson didn't discover relativity,
but he created the ground on which relativity could stand. He received the Nobel Prize in 1907. The citation praised his optical precision instruments and the spectroscopic and metrological investigations carried out with their aid. They gave him the prize for his instruments, for his precision, not for what he found, for how well he looked. And perhaps that's fitting, because Michelson showed us something profound. The quality of your measurement determines the depth of your insight. In science, how carefully you look is often more important than what you're looking for. Michelson and Morley looked for the ether wind. They didn't find it. And in not finding it, with such precision that doubt was impossible, they found something far more valuable. A crack in the foundation of physics, wide enough to rebuild the entire structure. That's the lesson. Sometimes the most important discoveries begin with the word, that's strange. I expected something different. And sometimes failure, measured with sufficient precision, becomes truth. In the basement of Adelbert Dormitory at Western Reserve University, mounted on 5 feet of sandstone floating on a pool of mercury, was an instrument designed to measure our motion through the cosmic ocean. It found no ocean. For decades, this was considered a failure, the most famous null result in physics, an embarrassment to its creators, a puzzle without solution. But we understand now what Michelson and Morley actually accomplished. They didn't fail to detect the ether. They succeeded in detecting space-time. They didn't fail to measure Earth's motion. They succeeded in proving that motion is relative. They didn't build a machine to confirm what we knew. They built a machine that revealed what we didn't know we didn't know. The universe, it turns out, is not like we imagined. There is no cosmic stage, no absolute rest, no invisible substance carrying light. There is only space-time, dynamic, flexible, relative. And light, which needs nothing to carry it because it is woven into the structure of reality itself. The Michelson-Morley experiment broke reality, but what it revealed beneath was far more beautiful than what we lost. Space and time are not separate. Motion is not absolute. Light is not mechanical. These aren't complications. They're simplifications. Elegances hidden beneath our intuitions, waiting for someone to measure carefully enough to find them. In 1887, 2 men built a perfect machine to answer the wrong question. And in answering that wrong question perfectly, they gave us the right answer to a question we hadn't thought to ask. This is Cosmic Canvas, where we ask the wrong questions perfectly. Until next time, remember that not all failures are mistakes. Some are just truths, dressed in silence.